Today's video will cover sections 914 and 916. It'll be a problem based on Stokes Theorem and a problem based on Divergence Theorem. The first problem asks for a line integral z dx plus x dy plus y dz. And it's based on the path. Notice it's a closed path that's indicated by the circle on the actual integral sign. The path is formed by taking a cylinder, x squared plus y squared, which is this cylinder here, equals 1, has a radius of 1, in the plane y plus z equals 2. Now, this beige area here is actually the plane y plus z equals 2, and it's the plane that cuts across, kind of at a diagonal, cuts across the actual cylinder and forms this surface. And that's the actual path, this oval path that you're seeing here. What you need to realize is this line integral, actually, you can imply two things. There's a product of there's the actual force field, which is determined by z I hat plus x j hat plus y k hat, and that is indicated by the coefficients, if you will, in front of the dx, dy, and dz, the variables in front of those three. Also realizing that dr in general is always dx I hat plus dy j hat plus dz k hat. Now, these two things are kind of subtle, but you need to realize that that's what this is actually doing. This is actually taking the next step, and it's rewritten as closed path integral of f dot dr. And if you do this, and keeping these two things in mind, you actually get the line integral that you have here. You've got to take a presence of mind to actually realize this is what's going on here, and what you're actually calculating is the force times the distance around a closed path. In this case, the work done. So for Stokes Theorem, which says you can use Stokes Theorem to calculate the work done around a closed path, the path must be closed. There's a right side of that equation which says it's equal to the double integral of the curl of f dotted with n hat ds, where this is the surface that is formed by the closed path. The closed path that's being traveled in calculating the work done of the force field. If you notice, the right side has essentially three components that need to be found, and it's the curl of f, the n hat, and the ds. It's very mechanical at this point by finding each one, and you just plug back in as you find each one. The curl of f is equal to, if that's your f, I'm going to assume you know how to do the curl, you should get equal to I hat plus j hat plus k hat, each having a coefficient of 1. N hat is determined by, I'm going to go ahead and tell you what the formula is, gradient of g over the magnitude of g. Now let me explain to you what g is. N hat is a vector that is normal to the actual surface at every single point. There's your n hat, and it looks something like that. It could point outward or inward, but upward or up or down. In this case, we're pointing upward because that's usually the standard. So we need to form n hat based on this surface. Well, what g is a function x, y, z, which is actually a level surface that describes this actual surface in question here. So g of x, y, z must be based on this. You must form a level surface based on this actual surface. In order to do that, we say, well, you look at this y plus z, that's the equation of this plane, which is formed by cutting the cylinder here. So g of x, y, z would be all x's and y's and z's that are on the same side of the equation. In this case, all we have is a y plus a z. Therefore, the gradient of g is going to be equal to j hat plus k hat. And similarly, the magnitude of the gradient would be equal to the square root of 2, assuming you know how to do both gradients and the magnitude of that. Therefore, the actual n hat vector is going to be equal to j hat divided by the square root of 2 plus k hat divided by the square root of 2. The last piece of the right side of this equation would be to establish what ds is. And as we've seen before, ds is some factor multiplication of dA, where dA is the projection of the actual plane, the actual surface onto the xy plane in this case. What you need to realize is we're not looking for a g function level surface per se. We're looking for the actual surface described, not in terms of a level surface, but the actual surface itself. So I'm going to put the gradient of f, where f is the actual surface described by this equation, which is, in general, f of xy is equal to z. Based on this equation here, we can say that that's going to be equal to 2 minus y. Now, the reason that's important is because we want to find the gradient of that surface. So the gradient of f is going to be equal to 0 I hat minus j hat plus k hat. Now, if you're wondering why it's plus k hat, because if you take the partial derivative of f with respect to z, which is the k component, you will get a 1. Therefore, the magnitude of the gradient of f will be equal to the square root of 2. And that's by taking the square of each component and taking the square root of the sum of those squares. So, at this point, then, we can say that ds is equal to the square root of 2 multiplied by, I'm going to go ahead and say that dA, since dA is a projection onto the xy plane, dA is going to be dx times dy. Now we're ready to plug in all the components back into this right side of the equation. Therefore, the work done using Stokes Theorem around the closed path f dot dr is equal to the double integral of the curl of f, which winds up being I plus j hat plus k hat, dotted with the n hat vector, which is j hat over square root of 2, j hat over root 2, plus k hat over root 2, multiplied by ds, which is all of this here, square root of 2 dx dy. And of course, since we're talking about dx dy, we're talking about the limits of integration in the xy plane. If you notice that's a circle, we're going to go ahead and change that into polar coordinates in just a minute. At this point, I want to actually do the line integral, not the line integral, but the dot product as shown in this step here. So I'm going to get equal to, this simplifies to the double integral of I hat plus 0, I hat dotted with 0 I hat, of course, is a 0, j hat dotted with 1 over root 2, j hat winds up giving you 1 over root 2, plus k hat and k hat gives you 1 over root 2, times root 2 dx dy. Now, if you notice, the root 2's will cancel, but you have these numerators that add up to 2, so this actually simplifies to double integral of 2 dx dy. Now, switching this to polar coordinates, I can say that that's the same thing as saying equal to double integral of 2 r dr d theta, where this is the same as your dA. At this point, I have my limits of integration in terms of radius and in terms of angle theta, so that becomes double integral 2 r dr d theta, where your r goes from 0 to 1 and your theta goes from 0 to 2 pi, because we're talking about the entire circle here. Of course, radius goes from 0 to 1 and theta goes all the way around the entire circle. That, when you do the calculation, should wind up giving you 2 pi. So the answer for this is 2 pi. Notice that that is the work done, so it'll have units of joules or units of work altogether. Notice it is a scalar value, because if you come back and do the dot product, you should get a scalar value. And of course, integrals in general just wind up giving you scalar values as well. Okay, the next problem deals with divergence theorem. Now, what you need to realize is the divergence theorem is used to solve for flux out of an enclosed volume, and I would say it's a volume that's enclosed by a surface. So notice this is a surface of a dome with a surface on the bottom of this dome, and we're asked to calculate how much of that force field, this force field, is exiting, i.e. the flux, through this surface. So once you establish that you have a closed surface that encloses a volume, we want to know the flux of F through all sides of that enclosed volume. So divergence theorem does deal with a double integral. It's an enclosed surface, so I'm going to put this, which indicates that we're talking about a surface area that encloses, that's closed, of the flux, which is F dotted with an n hat ds, and that's going to be equal to the volume that this surface encloses of the divergence of F. Of course, since we're talking about a volume, it's got to be dV. What this is saying here is if I have a couple of surfaces here, I have this dome and the floor that encloses the volume. Technically, the left side would tell me that I have to calculate the flux through both surfaces, this one and then this surface over here. The right side winds up being a simpler way because all you have to do is calculate the divergence of F in the entire volume and then figure out what the volume is altogether. So the right side simplifies what the left side is doing, but they both do the exact same thing. What I mean by that is this is going to be equal to the flux. The left side is going to be equal to the divergence of F. Well, the divergence of F is equal to 1 plus 1 plus 1, assuming you do the divergence of the right side here. That's going to be equal to 3. What that translates is that the right side then becomes triple integral divergence of F, which is just 3 of dV. Now I have dV, which is, I'm calculating the volume of this hemisphere sitting up here. Notice limits of integration start from z equals 1 to z equals, 1, 2, 3, 4, z equals 4. So the actual volume, since I'm talking about a sphere, this simplifies to 3 triple integral of dV, where this right here would be the volume of this object. Well, if you can remember this, and these are kind of tricks of the trade here, if you can remember that the volume of a sphere is 4/3 pi r cubed, and we're talking about a half sphere, then we need to take half of that, where the radius is going to be the radius of this whole sphere, which is from 1 to 4, which has a radius of 3. This winds up being 3/4 pi 3 cubed times 1/2. Of course, by simplification, you can say this 3 cancels with that 3. This 2 turns that, this 4 and times a half turns that into a 2. So this winds up being 2 pi times 27, which winds up giving you a total of 54 pi. What that means is, in terms of flux units, that means is that the left side is equal to 54 pi because the right side is equal to 54 pi. So the total flux through the entire, both surfaces together, is going to be equal to 54 pi. As you can see, this winds up being a pretty simplified way of calculating the left side by using the right side. And that is the use of divergence theorem.